Welcome back. In this video, we are going to finish chapter 1 with section 1.6 about product spaces. Okay, so recall that if you have n sets, x1, x2, xn, the set of n tuples, x1, small x1, etc., small xn, where each component belongs to the corresponding space, is what we call the Cartesian product of these sets. And we denote it by x1 times x2, etc., or by this symbol product I from 1 to n of capital Xi. Now, in particular, suppose that these sets are topological spaces. So there is a topology on each of these sets. We want to put a topology on their product. So this is done in the following way. Let us first define the notion of an open rectangle. Now, I am calling it open rectangle because it's easy to visualize, but actually it's called a basis element of the topology. So an open rectangle, according to us, is just a product of open sets where each term is an open set of the corresponding space. Okay. Now I'll give an illustration. So then the product topology on the product is defined as follows. A set in the product, a set O in the product is said to be open if whenever we have a point in that set, there is an open rectangle containing X and contained in O. So this really looks like the definition of an open set in a metric space, but here instead of a ball, we have the notion of open rectangle. So it's very similar actually. Okay. So we have to check that this is really a topology. But this is, let us illustrate this, what do I mean by that? And just in the case of n equal 2, just the product of two topological spaces. So this is the set O. What do I mean by a set is open? If for every point x in the set O, so x is actually a couple, x1, x2, it has two coordinates in this case, then we can find an open rectangle. This is why we call it a rectangle, okay? Because this is the product of two open sets. So the sides of the rectangle are just U1 and U2, and U1 is open in x1 and U2 is open in x2. Okay, so this is, if you like, a substitute of the notion of ball. Okay, so instead of balls, we take rectangles. Okay, so let us check that this is really a topology. So it satisfies the three properties of a topology. So we have to check that the empty set and the whole space are open. An arbitrary union of open sets is an open set, and the intersection of two open sets is an open set according to our definition. And of course, if we just prove it for two, intersection of two, we can then use induction to prove it for an arbitrary number of, that's finite, of course. So, but the proof actually is just a copy of the proof of proposition 1.2, where we proved that the collection of open sets satisfies the three properties of a topology. Okay. So first of all, the empty set is open just because it contains no point. So because the condition is an if condition. So if we have a point, then we can find an open rectangle. But so if you don't find any point, then it's true. And the whole space is open because actually the whole space, the product actually is an open rectangle itself, because the product of xi, each xi is open in itself. So the product of xi is an open rectangle according to our definition. Okay. Now the union of open sets is an open set. So we have to check that the union satisfies the condition of openness. So we take an arbitrary point of coordinates x1, xn in the union. Then this point is in some of them. So is in some O mu. Okay. Now O mu is open. Is an open set of the product. So we can find an open rectangle containing this point x1, xn, and contained in O mu. And it's therefore contained in the union because the union contains O mu. Okay, so x belongs to the rectangle and the rectangle belongs to O mu, and O mu is contained in the union. So it's really straightforward. And what about intersections? So just take two open sets in the product, O1, O2, and take a point in their intersection. Now, by definition, we can find an open rectangle that we call product of Ui containing X and contained in O1. And similarly for O2, because O2 is open, we can find another open rectangle that we denote by product of Vi containing X and contained in O2. And now, if you intersect these two, product of U1 intersect with product of Vy, product of Ui intersect with product of Vi, simple set theory tells you that the intersection of this rectangle with this rectangle is again a rectangle, an open rectangle. Okay, so the intersection of this product is the product of the intersections. Okay, it's straightforward. And now this rectangle, and actually you can see it geometrically. The intersection of two rectangles is a rectangle again. Okay, it's an open rectangle. And the intersection is contained of these two rectangles contained in the intersection of O1 and O2. So this is really straightforward. And this is actually a little bit simpler than the proof that the intersection of two open sets in a metric space is open, because the intersection of two balls generally is not a ball. But the intersection of two open rectangles is again an open rectangle. Okay? Because if Ui is open and Vi is open, their intersection is open in the space capital Xi. Okay, so this is really straightforward. Okay, now let us record an important fact that, which is the first one is trivial. The product of open sets in a product, of course, is an open set, and the product of closed sets is a closed set. So this is expected. Now, the first point is trivial because a product of open sets is by definition an open rectangle. And if you notice, an open rectangle is itself open. So this is like the fact that when we prove that an open ball is an open set. So here we have something very similar, but actually simpler. Okay, why an open rectangle is an open set? Because if you take a point in the open rectangle, then you take as another open rectangle the open rectangle itself. So this is really trivial. Okay, so it's like when we proved the first point that the whole space is open. Okay, so the idea is similar. Okay, so an open rectangle is an open set. Okay, I'm saying I didn't write it, but it should be clear that an open rectangle is an open set. So therefore, a product of open sets is an open set. So this is just another way of saying an open rectangle is an open set. Okay, now less trivial, the product of closed sets is a closed set. Okay, so we go back to the definition. Okay, a closed set is a set whose complement is open. So we have to prove that the complement of a product is open. Okay, so of course you just do it for two, because then we can do it for any number by induction. So just take two spaces, x1 and x2, and take a closed set A in x1 and a closed set B in x2. Okay. Then simple set theory tells me that the complement of this of A times B in the product is what? Is the union of two open rectangles, actually. Here we can draw a picture if you like. So this is just a set theoretical identity. So a couple, let us say x1, x2, small x1 or xy if you like. Small x1, small x2 is here, so it's not in AB. It means that either the first one is not in A, this is just A, not A1. So either what does it mean that a couple xy is not in A times B? It means that either x is not in capital A or small y is not in capital B. Okay, so this is, so it's x1 without A times x2 union x1 times x2 minus B. Okay, so, and now if A is closed, the complement is open in x1. So this is open times open, and this is open times open. So it's the union of two open sets, and therefore it's open. Okay, and now let us restrict ourselves. The final result is in the special case where each space xi is itself a metric space. Okay, because here it was very general. We just talk about topologies. Okay, so no metric was involved. Okay, but now what if we have n metric spaces, usually different? So we have a distance on each set. So d1, d2, dn. Okay, and consider their product, their Cartesian product. And now we can put actually several distances on the product. So I will just define 3 of them. The sum of the distances, it's like the one norm that we talked about earlier, and the Euclidean distance, if you like, sum of the di squared raised to the power 1/2, and the maximum distance. Okay, so now you are asked in the exercises to prove that ρ1, ρ2, ρ∞ are distances. Okay, so they satisfy the 3 properties. They are distances on the product actually, okay, because now each x is an n-tuple and y is an n-tuple. And this is not difficult actually. So they are distances, and actually, moreover, they are topologically equivalent, and they generate the product topology that we defined earlier. Okay, so there's something to do here. So I suggest that you try to do it on your own, because you cannot learn just by watching videos. You have to make your hands dirty. So you have to prove several things. Okay, so ρ1 is a distance, ρ2 is a distance, ρ∞ is a distance. Now, second thing, they are topologically equivalent. Actually, they are Lipschitz equivalent, if you like. So just more. Okay, so try to be inspired by the proof of a previous proposition when we talked about nuls on Rn. Here is something very close. Okay, so for example, ρ∞ is less than ρ1. Okay, because this is the maximum, this is the sum. And ρ1 is less than n times ρ∞. So this double inequality tells me that ρ1 and ρ∞ are Lipschitz equivalent and therefore topologically equivalent. And you can do something similar between ρ2 and ρ∞. So exactly like we did before. Try to write them. Okay, and last thing, you have to choose one of them, for example, ρ∞ or ρ1, and prove that ρ1 generates the product topology that we just defined in the beginning of this video. Okay, so this concludes section 1.6, and therefore chapter 1, which was a lengthy chapter, the lengthiest chapter in this course. Now, from now on, the remaining chapters will be shorter, actually. Okay, but this chapter was lengthy because it contains a lot of jargon and concepts, and so this is the language of topology, if you like. Okay. So thank you for your attention, and in the next video I'm going to solve the remaining exercises of chapter 1 and finish this chapter. So thank you for your attention.